Welcome to the session on integration, indefinite integrals. The objectives for this session are to find y given dy dx for x to the power n, integrate polynomials, and find f of x given f dash of x and a point on the curve. Do note that if you have covered the session on integrating polynomials, then a considerable portion of this session will be identical to it. The portion that is identical will be indicated by the word review written in the left-hand corner of the screen. Recall the rule for differentiating x to the power n. If y equals x to the power n, then dy dx equals n times x to the power n minus 1. The reverse of differentiating is integrating, and the rule for integrating x to the power n is if dy dx equals x to the power n, then y equals x to the power n plus 1 divided by n plus 1. Integration is the reverse of differentiation. So what do we do if we want to differentiate? We start with, say, x to the power n. We multiply by the power and then subtract 1 from the power to give n times x to the power n minus 1. And what do we do if we wish to integrate? We start with, say, x to the power n, then add 1 to the power, and then divide by the power, so that we are left with x to the power n plus 1 divided by n plus 1. X to the power n, or x to the power n plus 1 divided by n plus 1 is the function, and the gradient function is respectively either n times x to the power n minus 1 or x to the power n. Now, integration is the reverse of differentiation. Before we go into any more details, let's take a look at 3 more examples. Y equals x cubed plus 6, y equals x cubed, and y equals x cubed minus 1. All 3 functions are different. However, when we differentiate, we obtain dy dx equals 3x squared for each of them. So when differentiating, constant terms disappear. Functions which only differ by a constant differentiate to give the same function. Therefore, when we integrate, we must add a constant of integration at the end of a function. So when we integrate dy dx equals 3x squared, we obtain y equals x cubed plus c. And notice here we've added a constant of integration. So, if f dash of x equals x to the power n, then f of x equals x to the power n plus 1 divided by n plus 1 plus c, where of course n does not equal minus 1. Let's take a look at integrating x to the minus 1. We cannot use this rule that we've indicated here if n equals minus 1, since 1 over n plus 1 is undefined at n equals minus 1, as we cannot divide by 0, as you can see from these formulae. We will look at how to integrate x to the minus 1 in a later session. Let's now take a look at some examples. Find y for the following. Part A, dy dx equals x to the power 6, and part B, dy dx equals x to the power minus 3. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 1a first. The rule which we will be using has been highlighted. Since dy dx equals x to the power 6, when we apply this rule, we add 1 to the power and then divide by that new power. So we now have x to the power 6 plus 1 divided by 6 plus 1. And of course we must add the constant of integration, c. Here's the value n plus 1. And this becomes x to the power 7 divided by 7 plus c. Now let's solve part B. Again, we add 1 to the power and then divide by the new power. So here's n equals minus 3. So our new power is minus 3 plus 1. And this tidies up to x to the minus 2 divided by minus 2 plus c, which is of course equal to minus a half times x to the minus 2 plus c. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. Again, the rule which we are applying has been highlighted. So n plus 1 is a third plus 1. And tidying up gives us x to the power 4 over 3 divided by 4 over 3 plus c. And when we're dividing by fraction, we multiply and flip the flat fraction over. So we're now left with f of x equals 3/4 x to the power 4 over 3 plus c. Now let's have a go at example 2b. F dash of x equals 5, and another way of expressing this is 5x to the power 0. So n equals 0, and therefore f of x equals 5 times x to the power 0 plus 1 plus c. Therefore, f of x equals 5x plus c. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Before we begin, remember that when integrating polynomials, apply the rule for integration separately to each term. So, dy dx equals x to the 4 plus 3x squared minus 4x to the minus 3 over 2 implies y equals x to the 5 over 5 plus 3x cubed over 3 minus 1 minus 3 over 2 times 4 times x to the power minus 3 over 2 plus 1 plus c, which tidies to x to the 5 over 5 plus x cubed plus a half times x to the power minus a half plus c. It is possible to find the constant of integration c when you have any point xy that the curve of the function passes through, or any value the function takes. To find c, integrate the function and substitute values xy of a point on the curve or the value for function at a given point, f of x equals k, into the integral function. Then solve the equation to find c. Let's take a look at an example. Given that dy dx equals x squared and point 23 passes through the curve, find y. Let's solve this. Here are the rules for integration, in case you've forgotten and for reference. Now, dy dx equals x squared. So how did we obtain y equals x to the power 2 plus 1 divided by 2 plus 1 plus c? Let's see how the rules of integration apply. So here we've added 1 to n is equal to 2, so n plus 1 equals 2 plus 1. And when we tidy up, we obtain x cubed over 3 plus c. So y is equal to x cubed over 3 plus c. Now we know that 2, 3 passes through the curve. So let's substitute that into the equation. Here's y equals 3, and here's x equals 2. And therefore, rearranging the equation gives us that c equals 1/3. And therefore, y equals x cubed over 3 plus 1/3. Let's now take a look at what various x cubed over 3 plus a constant curves look like on the xy axes. Here's y equals x cubed over 3 plus 2. And here's our curve, y equals x cubed over 3 plus 1/3. Notice it has shifted down. And here's y equals x cubed over 3 minus 4, which has shifted down even further. And here, of course, is our point 2, 3, showing that our curve is passing through it. Now let's take a look at another example. The curve C, passing through the point 4, 24, has equation y equals f of x. Given that f dash of x equals x cubed plus 3 all over root x, find the equation of C. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Here's our f dash of x. We're going to rewrite this so that we're able to integrate it. So x cubed over root x becomes x to the power 5 over 2. Essentially, we're saying x to the power 3 minus a half. And 3 over root x becomes 3 times x to the minus a half. And now we can integrate. Again, here are the rules for integration in case you need a reminder. We're going to use the highlighted law for integration. So add 1 to the power of x and then divide by that new power. So we have x to the power 5 over 2 plus 1, all over 5 over 2 plus 1. And similarly for the second term, 3 times x to the power minus a half plus 1 divided by minus a half plus 1 plus c. And then tidying up gives us 2 over 5x to the power 5 over 2 plus 6x to the power half plus c. However, we know that f of 4 equals 24 because the curve that we're interested in passes through the point 424. Therefore, plugging these values in, here's x equals 4, and here's f of x equals 24, or y equals 24 at that point. And rearranging this equation gives us that c equals minus 0.8. And therefore, our function is f of x equals 2/5 x to the power 5 over 2 plus 6x to the power half minus 0.8. This brings us to the end of this session. If you have understood its contents, you should be able to find y given dy dx for x to the power n, integrate polynomials, and find f of x given f dash of x and a point on the curve. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.